Greetings to the distinguished guests, session chairs, and fellow researchers. My name is Siddhi Chade, and on behalf of our team at Computer Science at PES University, Bengaluru, India, I'm honored to present our work at IEEE ISDFS 2026. Our paper is titled A Controlled Comparative Study of MongoDB Security under REST and GraphQL APIs with Proxy Based Protection. In this presentation, we will briefly cover the problem that we are solving, the framework we designed, and the results we obtained. Modern applications today rely on three technologies that have become almost a standard: NoSQL databases for a flexible and high throughput data storage, REST APIs for a structured communication between systems, and GraphQL APIs for dynamic client driven data queries. Among NoSQL databases that are there, MongoDB has emerged as one of the most widely used solutions because of its document oriented design and its capability to scale horizontally. However, this architecture also introduces security risks. If APIs fail to handle user input properly, attackers can exploit these vulnerabilities through NoSQL injection attacks, which may allow them to bypass authentication or access sensitive data. In more severe cases, these vulnerabilities can also enable DOS attacks, that is, your denial of service attacks, potentially overwhelming or halting the server, thereby decreasing the availability. Since MongoDB is commonly accessed through REST and GraphQL interfaces, understanding how these core API architectures differ in their exposure to such security risk is become increasingly important. So why do we need to compare REST and GraphQL security? REST and GraphQL differ fundamentally in how they expose the data. REST uses multiple fixed endpoints, each handling predictable, well scoped requests. GraphQL, by contrast, uses a single endpoint that accepts flexible client defined queries. These structural differences have high security implication. REST distributed endpoints create a larger but more compartmentalized architecture for the attack surface. GraphQL single point centralizes control but enables deeply nested, intensive queries, a property that the attackers mostly used to exploit. However, response structures also differ. REST returns fixed formats, while GraphQL returns only what the client requests, introducing schema introspection risks that can reveal sensitive API internals is one of the common threats that we can see in GraphQL architectures. These are not hypothetical distinctions that I am stating. They are directly something that attackers are using actively to figure out how to exploit the systems that we are using. Despite how widely used these APIs are today, most existing research studies them in isolation. There is work on REST API, studies on document GraphQL vulnerabilities, and research focusing specifically on MongoDB security. However, what is missing is a direct comparison of how MongoDB behaves from a security perspective. When accessed through REST versus GraphQL under the same backend conditions and equivalent attack scenarios. In addition, there is currently no lightweight mitigation framework that can protect both architectures simultaneously without requiring modifications to the underlying backend services. Our study aims to fill this gap through a controlled empirical side by side evaluation of REST and GraphQL, focusing on two major attacks, namely your injection attacks and your denial of service, while also introducing a unified protection layer that works across both these architectures that I just stated. Okay, so what is our research objectives? Our study was guided by four key research objectives. Firstly, we want to compare the MongoDB security when accessed through REST and GraphQL while keeping the backend conditions exactly the same. Second, We aim to identify and simulate key vulnerabilities, particularly injection and DOS, that is your denial of service attacks, across both the API architectures, namely your GraphQL and REST. Third, we designed a reverse proxy security framework that intercepts and filters malicious requests before they reach the backend, integrating a machine learning classifier to detect no SQL injection attempts in real time without requiring any changes to the existing API. And finally, we evaluated the effectiveness of this framework through a controlled attack simulation and performance benchmarking. Together, these objectives form an end to end contribution, starting from the vulnerability identification and moving all the way to the empirical validation of our mitigation approach. So, what is the proposed security framework that we are talking about? At the heart of our solution is a reverse proxy security layer that is positioned between the client and the API servers. This means that every incoming request, whether it's targeting the REST interface or the GraphQL interface, passes through the proxy first. The proxy performs two main inspections. First, it uses a machine learning model to detect injection attempts, analyzing the query payload, assigning a probability score that indicates whether the request may be malicious. If a request is classified as non malicious, it is simply forwarded to the backend API. If it is detected as malicious or exceeds a certain execution time, it is blocked immediately before it's reaching the server. Now, the performance based timeout that I just spoke about is for denial of service attacks. It helps us monitor how long a request takes to execute and terminate that exceeds a predefined execution threshold. The main idea behind this design is to keep the solution simple and practical. The proxy sits in front of the APIs and can protect REST and GraphQL at the same time. And importantly, it does not require any changes to the backend services, which makes it easier to deploy on the existing systems. Now, I will hand over this to Tejas, who will present the rest of the sections.
Thanks, Siddhi. So I'm Tejas Gaurish. Let me begin by defining the system architecture that governs our experiment. So the end-to-end architecture comprises of three layers. The client layer, which involves web and mobile applications. The traffic passes through the reverse proxy security layer, which hosts the ML injection classifier, as you saw in the diagram in the previous slide. So cleared requests are passed to the API layers where they are processed and sent over to the MongoDB backend. So we have two API server setups, one being the REST API server and the other being the GraphQL. So malicious requests are blocked at the proxy layer and they never reach the application servers. So this allows legitimate traffic to pass through while blocking malicious traffic. Moving on to the threat model, we assume attackers have access to both API endpoints, and we assume they can craft and submit arbitrary requests, automate requests to maximize impact. And we also haven't implemented client-side validation to simulate a true attack environment. So there are three categories of attacks that we model. NoSQL injections being the first. Crafted payloads designed to bypass MongoDB authentication or manipulate query execution, enabling unauthorized data access or corruption. Second, denial of service. Resource exhausting queries and recursive request patterns aimed at overwhelming server and memory. GraphQL specific attacks. So deeply nested query chains, circular resolver paths can exploit GraphQL's flexible single endpoint architecture. So attacks that are out of scope are the operating system level, model poisoning, and physical access to the API servers. So for the experimental environment, we deployed two intentionally vulnerable API servers, as mentioned before, both connecting to the MongoDB instance. Critically, neither server included any input validation, sanitization, rate limiting, or schema validation. This was done to simulate real world vulnerabilities that lie in databases and database servers. So both APIs expose the same social media data set containing users, posts, likes, and comments, and relations for the same. We conducted our experiments on an Intel Core i7 processor with a 16 GB RAM and a 64-bit operating system. The MongoDB server was deployed locally along with the API servers as well as the client systems. So we crafted semantically identical data sets targeting both the GraphQL and the REST API servers. So this was done to simulate identical attacks across both interfaces. So the data set consisted of 2008 queries, 406 being malicious and about 1602 being benign. So these were sourced from the MongoDB injection dataset uploaded by Islam and others. And we augmented this dataset with semantically identical GraphQL queries, as mentioned before. So we address the class imbalance using class weighting on the SGD classifier in our model, which penalizes misclassification of minority class samples more heavily without altering the original data set. And feature extraction combined two complementary approaches, character level TF-IDF n-grams, capturing n-grams of length 2 to 4, and structural features, including operator frequency, query depths, syntactic imbalance, and other semantic anomalies. We trained the calibrated SGD classifier with a log loss and L2 regularization and validated using stratified k-fold cross-validation on a holdout test of 20% test set of 402 samples. So the train model outputs per request malicious probability scores. Requests exceeding the classification threshold are blocked by the proxy, and all others are forwarded to the backend. Moving on to the vulnerability results. The state of the MongoDB security before the proxy was deployed. Starting there, every single crafted injection payload succeeded on both GraphQL and REST API interfaces, implying a 100% attack success rate. The average response times before deploying the proxy was 75.2 milliseconds in REST API and 98 milliseconds in GraphQL. So moving on to DOS, both servers were ultimately brought down. The server crashed in 62.45 seconds for REST and 82 seconds for GraphQL. So both results establish that in the absence of defensive controls, both REST and GraphQL expose MongoDB to full exploitation. Although the architectural differences between them do not by themselves provide any meaningful security protection. Turning to the performance of our ML classifier, the SGD model achieved an accuracy of 98.26%, consistent with our cross-validation results. The F1 score of 0.956 demonstrates strong balance between precision and recall. The ROC-AOC curve of 0.998 indicates a near perfect discrimination between malicious and benign queries across all classification thresholds. Most critically for a production environment, the true positive rate was 93.83%, meaning the vast majority of attacks were caught, and the false positive rate was just 0.62, meaning legitimate traffic was almost never incorrectly blocked. A low false positive rate is essential in a real-world attack scenario. Classifier that aggressively blocks legitimate requests is not deployable. Our model demonstrates that high detection accuracy and low operational disruptions are simultaneously achievable. Now I hand it over to Ullas. Thank you.
Thank you, Tejas. My name is Ulas. I'll be taking you through the results and findings of our research. Uh, with the proxy deployed as a single endpoint, we ran identical workloads. The results were decisive. For injection, the proxy blocked almost 100% of the malicious injection attempts across both REST and the GraphQL interfaces, across 50 repeated login attack simulations per interface. Complete mitigation was achieved. The latency overhead introduced by the proxy was very minimal, and for both REST and the GraphQL, as you can see by the numbers on your screen. For denial of service, a 30-second timeout threshold at the proxy level terminated long-running and circular queries before they could exhaust the server resources. REST average response time before failure dropped from 62.4 to 30.8 seconds, almost a 51% reduction. GraphQL as well dropped from 82.31 to 30.11 seconds, a 63% reduction. Servers remained available, which was the most important part, and memory exhaustion was prevented. Beyond the aggregate results, our control setup allowed us to draw nuanced comparative insights about the security characteristics of both architecture, REST versus GraphQL. REST offered predictable, well-defined endpoints, making injection patterns more structurally consistent and easier for the classifier to detect. However, it exposed multiple exposed routes, created a larger distributed attack surface. The recursive route abuse can be an effective DOS vector when it comes to REST API. GraphQL's centralized schema provided an opportunity to enforce deep limits and type constraints at the schema level. However, the flexibility of its query model makes it inherently more susceptible to nested query DOS attacks and schema introspection. The key takeaway from this comparison: neither architecture is inherently more secure. Each has distinct attack surfaces and mitigation opportunities. Our proxy framework addresses both simultaneously, but each architecture also requires architecture-specific hardening, strict operator filtering for REST, and depth limits and schema control for GraphQL. To summarize the contributions of this paper, first, this is the first controlled empirical comparison of MongoDB security under REST and GraphQL under identical backend conditions. Second, we developed a unified threat model covering injection and DOS attack vectors for both these architectures. Third, we designed a lightweight reverse proxy framework that protects both APIs simultaneously, requiring no backend modifications. And fourth, we delivered an ML-based injection detection classifier, achieving 98.26 accuracy with a false positive rate of just 0.62. And fifth, we provided empirical validation through real attack simulations, demonstrating significant security improvements with manageable performance overhead. In conclusion, both REST and GraphQL APIs expose MongoDB to injection and denial of service attacks when security controls are absent. GraphQL's flexible query structure specifically amplifies susceptibility to query-based DOS attacks in the absence of depth control. REST multi-point edge design increases injection exposure if validation is inconsistent. These results reinforce a broader principle. Layered security architectures are not optional, they are mandatory. Looking ahead, our work opens up several avenues for future investigations. The ML classifier can be extended to detect additional attack patterns beyond injection. This includes schema enumeration, authorization bypass, and complex query abuse. The training data set can be enriched with real-world adversarially generated payloads, including obfuscated and encoded injection attempts to improve generalization to novelty attacks. The DOS mitigation strategy can evolve from static timeouts, adaptive query complexity analysis, dynamically calibrating thresholds based on the schema structure and server capacity. And finally, the framework should be evaluated against additional NoSQL databases and API frameworks in production-like environments to establish broader applicability beyond the MongoDB REST GraphQL context. Thank you all for your time.